show some sort of equivalence between this problem and this problem. Well, in the proof of the main result in fixed-point approaches, we don't actually treat this problem directly. We convert it to a equivalent summation equation and then work with that. Okay, so this is actually what we're going to work on rather than this. Okay, well, I haven't put this result of the proof in the notes that to appear in the JDEA, so I can discuss it in a little bit more detail now. So, okay, let X2 be a solution to this problem. What we can do is start with 1.1, move the H up there, and then sum up both sides. Okay, so I get something like this. And on the left-hand side, of course, the fundamental theorem of discrete calculus just gives you the following. Okay, so then you can just rinse to the side and you get the following here. Okay, so if we can determine what x sub naught, some expression for x sub naught, then we actually have our summation representation. Okay, so we take this sub in I little I equals m, and we have this. Now, what we can do is use the boundary conditions 1.2 to eliminate x sub in here. Okay, so using the boundary conditions, you can come up with the following, and then replace, so essentially you'll express x naught in terms of known things here, s and these constants. Okay, so instead you take x naught up there and replace it to get this big mess. Now, to clean it up a bit and to give it some nice properties, we can sort of recast it in this equivalent form, just by splitting this sum up. So sum from j equals 1 to I minus 1, and then sort of combine two sums into one. And you can come up with your summation representation 2.1. Okay, well that's proving it one way. If we let x tilde be a solution to this, then all we have to do is show that x tilde satisfies this, and then so basically take the difference of both sides and show that you get this, and then test the boundary conditions. So I haven't actually put that part in, but it's reasonably straightforward. Okay, so this is going to be a big part for us in the proof of the main result. Okay, so the following two lemmas or lemmas will be used again in the proof of the main result. Suppose Q is positive, and let G be the Green's function defined as 2.2. Then we have the following. Oops. Okay, essentially this is equal to this now. I haven't proved it. This is actually reasonably easy to prove this because G is a pretty simple function. It's a piecewise constant function, so you can take these sort of things outside the front of the summation, so that's reasonably easy to prove, so I won't do that. And the other result that we'll use is Hurley's inequality. Now, if you want to see a proof of this, then you can have a look at my YouTube video on that, which is in the references at the end. So suppose P and Q are both strictly greater than 1, and they satisfy this equation here. Then for all vectors in, say, Rcn plus 1, we have this inequality holds. And we'll use that a little bit later in the proof of our main result. Okay, well, our analysis of the boundary value problem will be set in the environment of what's known as a complete metric space. So if you want more details on a complete metric space, please see my video on YouTube about that. Essentially, the metric space is a set coupled with a way of measuring distance between two elements in that set. And a complete metric space is a special kind of metric space whereby special sequences called Cauchy sequences always converge to an element of the set Vx. So we're going to form the following complete metric space. We're going to consider the set Vx to be R to the n plus 1, and we're going to couple that set with a way of measuring distance between vectors in R to the n plus 1. The distance function or metric is defined in the following way. Now, P is just any positive, any number that's greater than or equal to 1 here. Okay, now, it turns out that this set coupled with this metric or distance function is a complete metric space. Okay, and again, I've proved that in this video. Okay, now, with respect to that fixed point theorem, which is what we're going to rely on in the proof of our main result, we need a little bit of terminology for that. So let Vx comma G be a complete metric space, and let F be some map that maps Vx back into itself. We say the mapping is constructive if there exists a constant alpha strictly between 0 and 1, such that for all pairs of points direction little y in our set Vx, the distance from f of x to f of y is less than or equal to alpha times the distance from little x to little y. Okay? The constant constant alpha is called the contraction constant of F. Okay, let's have a look at Banach fixed point theory. We're ready to start that now. Have a look at that. So this is a very famous fixed point theorem used by Stefan Banach in 1922. So suppose we have a pair, a set begets a distance function or metric, little d, which is a complete metric space. And suppose F maps the set begets that into itself and is a contractive map. So this holds some alpha between 0 and 1. Then it has what's known as a unique fixed point indicator. That is, there exists a unique element, u, in our set begets, such that f of u equals u. And if we define our sequence, fi of u, by starting with some arbitrary point or element indicates, and then having f operate on that point, so f1 of y is just f of y, f squared of y would be f of y, okay, and so on. Then the sequence converges to the unique fixed point for each starting value in our begets. And furthermore, and I'm not going to discuss this thing too much in this particular presentation, much more about the existence and uniqueness, but under the conditions of this Banach fixed point theorem, if we start at some arbitrary element, y in begets, then Banach's theorem provides an estimate of the error between the like information fi of y and the fixed point, namely this thing here. Notice this in terms of the contraction constant. So Banach's theorem does quite a few things. It gives you the existence of a unique fixed point, and it gives you a theoretical way of computing or approximating that fixed point through this iterative scheme. Okay, so on to the main result. The main result is as follows. The vector continuous and the coefficient in our boundary conditions satisfy u plus v not equal to 0. If there is this constant, L, delta, P, and Q, satisfying these conditions, such that the following three conditions are satisfied, then our discrete value problem 1.1, 1.2 has a unique solution for each h between 0 and this delta. So let me sort of deconstruct this a little bit to show you where these each condition comes from and what it's needed for. 3.1 is known as a Lipschitz condition on S. That's a very famous condition, and I have a video in the references talking about Lipschitz conditions and when it satisfies Lipschitz conditions and things of that nature. Now 3.2 is related to the contraction constant, alpha. Now it turns out that this big mess on the left-hand side is actually going to be the alpha in Banach's theorem. So you can see here, we want to show that big F is contractive, so we want to show an alpha exists between 0 and 1, so this is satisfied well. This is actually going to be the alpha. Okay, and finally, 3.3 is just related back to Holder's inequality. Okay, we needed this condition on our P and Q to invoke Holder's inequality. Okay, so let me talk about the proof now of this main result. The idea is to use Banach's fixed point theorem. Okay, so the first thing we need to do is set up a complete metric space. So here's our set, and here's our way of measuring distance between two vectors in R n plus 1. Now, this kind of general metric here is credited to Minkowski. Okay, now, the pair begets G sub P, where begets this, is a complete metric space, and the proof is in this video here, which you can look up. Summation equation with G is the Green's function here. Okay. Now, based on this right-hand side of the equivalent summation equation, we're going to define an operator T tilde, big T tilde. I probably should have written big F here or something, so I'm just going to write big T tilde. Essentially this right-hand side. Okay, so what you can see hopefully now is that if this has a fixed point, if T tilde x tilde equals x, then this is the same as that. So if we can show that there is a x tilde that satisfies this, then that's equivalent to that problem, which is equivalent to our original discrete DVP. So that's got to have a solution. Okay. So our focus now changes a little bit to this and showing that this has a so-called X point. So T tilde X tilde equals X tilde for some unique vector X tilde. Okay? So how do we show that this has a unique fixed point? Well, we want to use Banach fixed point theorem. Okay, well, we've got our complete metric space. We want to show that our operator maps, in this case, big R to the n plus 1 is R to the n plus 1, and we also want to show that it's contractive. So this is actually pretty easy to show, okay? The slightly more difficult thing is to show that we have a contractive map on our hands. Okay, so we want to show that there is a contraction constant alpha between 0 and 1 such that this is true for all vectors, pairs of vectors in R to the n plus 1. Okay, so what we want to do is sort of set this up and try to show the contraction. Okay, now, working from here, let X tilde and Y tilde be two vectors. Consider the following absolute difference. Let me help with this. Now, from here to here, we've used up to 3.1, which is just the Lifshitz condition on F in our main theorem. Where is it? Okay, this one here. Okay, so come with the following inequality. And then what we can do now is, you notice I've got a sum here of two expressions multiplied together. I can apply Hoda's inequality to this sum here. So essentially this right hand side can be made less than or equal to this. The sum P and Q should be greater than 1, which satisfy this. Okay? Okay, well, notice here that this is almost the d sub P of x by y beta. In fact, if I had another little sum here, it would be essentially less than or equal to x tilde y, d sub P x tilde y tilde. Okay, so what I've got now is this right hand side is in terms of this metric d sub P, and I'm going to try to express the left hand side in terms of d sub P of this. Okay, well, I can simplify what's in this big bracket just by the earlier lemma in section 2 to get the following. So I can just replace this with all of this. And then, again, I'm trying to form this on the left-hand side, so I can take to the power P and then sum up and take the whole thing to the power 1 on P. So, here I've got d sub P of this over this, not just this, so using my earlier inequality, I come up with the following, and if H is less than this, less than this delta, as in the theorem, then I've actually got a contractive map where this is strictly less than 1. Remember, this is one of the conditions of our theorem, 3.2. Okay? So, we've shown that our operator T tilde maps R to the n plus 1 into itself. I've got a complete metric space when I couple this set with this metric, and this working shows that our mapping T tilde is contractive. So all of the conditions of Banach 6.0 are satisfied. So what it means is that our mapping T tilde has a unique fixed point, and this yields the existence of a solution to a unique solution to our summation equation, which is equivalent to showing that there is a unique solution to our discrete boundary value problem, 1.1, 1.2. Okay, and I'll hand it over here, but you can go a little bit further and show that this sequence converges to a unique fixed point, and you have this error on the ith iteration, between the ith iteration and the unique fixed point. So that's the main result. So it's a reasonably abstract result, and it looks very general. What I'm going to do now is just choose some particular values of P and Q that satisfy this and this, and show you how 3.3, 3.2 simplify a little bit. So the following is a corollary. So the main result, just by choosing P and Q equal 2, and sort of repeating the argument in the proof, gives you the following. So that's continuous, and again these coefficients add to the some non-zero value. If there's just an L such that F satisfies this Lifshitz condition, that's the same from the previous. And there's some delta between 0 and n such that this is satisfied. Then 1.1, 1.2 have a unique solution for all h between 0 and delta. So you can see this is slightly simpler to this setup. Here P and Q are both equal to 2, so this is obviously satisfied, so I don't need that in my corollary. And this reduces down to this when P and Q are equal to 0. So I'm not going to discuss the proof too much here, I'll just list the main points, essentially to show that, again, we have a contractive mapping on our hands, and it turns out that this is your contraction constant. This condition ensures that the alpha is strictly less than 1. Okay. let me show you an example of the power of these results. In particular, I've just formed out an example showing the power of corollary 3.2. Essentially, the choice of metric in the proof of theorem 3.1 or corollary 3.2 ensures that a larger range of cells are admissible than, for example, another kind of metric. So here we have the match metric, defined in the following way. Look at the difference, the absolute value of the difference of each corresponding component of your vectors, and then you take the maximum. Just consider P equals Q equals 2, and then rerun the proof of, say, theorem 3.1 or corollary 3.2 with this particular metric. Then, instead of, say, this condition, you would get this condition. Now, this is a stronger condition than, for example, this one here. Okay, now let me give you an example of a discrete boundary value problem that satisfies, say, the conditions of corollary 3.2, but doesn't satisfy this condition here. I guess it shows that my results are a little bit more wide-ranging than Mohammed's. Okay, so let's just consider the following discrete boundary value problem. This is a special case of our original result with S defined in the following way, and our coefficients in our boundary conditions here and here, and begin equals 1. Now, you can show that this S does satisfy a Lipschitz condition with this L equals 8.5. Remember, this condition is just this condition here. And in this video, if you watch this video, you'll see why, essentially, because GF/GY is bounded by 8 on 5, and GF/GY is continuous. Okay? For more details, you can see this video here. You can show that the conditions of, say, corollary 3.2 are all satisfied for H between 0 and 1/4. Now, it's interesting to note that this condition does not hold, because if you calculate this with big L equals 8/5, big N equals 1, and U and V given here, you get 16 off this, which is not less than 1. So Mohammed et al.'s work doesn't apply to this example, but you can see that, or it can be verified, that the ideas in this